Give it one more second for the Zoom, the YouTube. All right, we should be good to go.
Medium
Whoop,
bad this
whoop. I lost it.
seems quite a bit, but
There I am.
occasionally it says this was never detected, and there's a
Are we ready?
Yeah, go ahead, John.
Oh, okay. Tonight, physicist Dr. Les Johnson is our guest speaker. He'll be talking about his work on solar sail propulsion for spacecraft, and there are many applications, from near-term science missions to study the sun and near-Earth asteroids to more ambitious missions to the edge of the solar system and beyond. He's also an established author of several science fiction novels, popular science books, and a member of the Science Fiction and Fantasy Writers of America. I have asked him to share some of his work with us. Please welcome Dr. Johnson.
Thanks, John. I appreciate you having me here tonight. I wish y'all had pretty skies to go out, but you don't. So I'll try to give you the consolation prize. How's that?
That's great.
Can you confirm that you let's see, can you see my slides?
Yes.
Awesome, great. Well, the first thing I have to say is tonight I'm speaking in my private capacity as a scientist and a writer. I do work for NASA at the George C. Marshall Space Flight Center here in Huntsville, but all my writing and lecturing about my books and topics, things like that, I do outside of work. So I'm not speaking on behalf of my employer. And please, if you're tweeting or anything like that, anything I say is my own opinion. So you can blame me. Don't blame my employer. So tonight, I'll be talking about this great topic that I have spent a good deal of my career studying and working on. And I've also had the pleasure of reading about and writing about in science fiction stories, and that's solar sailing. And I'll tell you what that is for those who may not be as familiar with the technology of solar sails. And I'll tell you what they can do, why they're important, and give you my vision for the future of solar sailing and why I'm motivated to participate in all this. By the way, if you're interested and you like my stuff, I am pretty much on social media, pretty out there on Facebook, LinkedIn, Instagram. I'm even messing around on TikTok and have had a few successful videos there for me. So anyway, just thought I'd pass that on, and my contact information is here if anybody'd like to reach out after the talk. So first off, let me begin, if I can get the slide to go, by correcting a misconception. And as an astronomy group, you probably know this, many of you do, but the general public tends to think of space as being big and empty. And generally speaking, if you're thinking about the kinds of stuff we interact with here on Earth, it is big and empty, but it really isn't. The deep space and near the Earth and the sun is actually pretty full of stuff. It's full of lots of energy. You have, of course, the sunlight, which we'll be focusing on, no pun intended, tonight in terms of the technology I'll be describing to you. But you also have coming out of the sun all kinds of radiation, both in optical wavelengths as well as particle radiation, the solar wind, which slams into the Earth and our magnetic field and creates the ionosphere. And if you were out last year about this time, you might have seen the aurora, which we actually saw here in Alabama, which I never thought I would see in my life. And that was due to a big coronal mass ejection from the sun. So there's lots of energy out there. And one of the things that has frustrated me about space exploration throughout my entire lifetime is we tend to approach space as something to get through to get to our destination. You survive space, you travel through space, and what people think of as important is the destination. Well, it turns out if you take into consideration all this energy that's out there, why take that for granted? Use it to your advantage. And we've been doing that with solar panels to generate electricity. We do that here on Earth and we do it in space, and it's how we power most of our spacecraft. But you can also use that light for propulsion, and I'll explain how. Spacecraft can use momentum of sunlight for thrust. Now, what you see here is an artist's concept of a solar sail. Looks like a small, tiny spacecraft there in the middle, attached to a large, thin, reflective sheet of aluminum foil. Well, solar sails are coated with aluminum because it's very reflective in the visible light, but it's about 100 angstroms of aluminum on a 2.5 micron thick, thin film, which is thinner than the saran wrap you get in your kitchen. And how does this work as a propulsion system? Well, it works like this. This is a piece of solar sail, And it's attached to a plastic backing to make it easier to hold, but you can hold it in your hand and crumple it up. If you try to tear it, you can tear it, but generally speaking, it's pretty robust. And so if you deploy a large sheet like this in space where the sun is reflecting from it, light is made out of particles, photons. Photons have no rest mass, but they do have momentum. And when they strike the sail, they reflect from it and they impart some of that momentum to the sail. For those who like to conserve energy, you might, which all of us do, whether you know it or not, you might be interested to know that the light that hits the sail after it reflects it is slightly redshifted. And it's redshifted because it lost a little bit of energy to the momentum and kinetic energy that it transferred to the sail. So how this works, if you study quantum mechanics and you're interested in drawing a force body diagram, you can understand it here if you understand Planck's constant, that photons have momentum. It's related to Planck's constant. And as it hits the sail, it gives some of that momentum to the sail. The brighter the sunlight means more photons, more momentum transferred. The dimmer the sunlight, the fewer photons, the less momentum transferred. You steer by tipping and tilting the sail. So if I'm looking at you and you're the sun, I put the sail out perpendicular, the thrust vector would be radially outward and would push away from you. But if I wanted to start going in this direction, I would tilt the sail like this so that I would still be moving out, but there would be a component of the thrust that would be pushing me in that direction. Similarly, tilting it like this, it would push me this way. Like this, it would push me up. And like this, it would push me down. Now, if you turn the sail sideways, you'd get no thrust, but we would lose control of the sail, so we don't ever do that. So now you understand how a sail works. You tip and tilt the sail to change the angle at which the light reflects from it. That's how you steer. Now, to characterize the performance of the sail, solar sail advocates had to come up with a way to talk about how efficiently the sail operates. When you're in space, you're still subject to Newton's laws. Force equals mass times acceleration. At a given distance from the sun and a sail of a certain size, if you're holding stationary, there's a maximum amount of force that sunlight can apply to the sail. So that force is going to be equal to the mass times the acceleration of the sail. So if you have a very heavy sail and spacecraft, you won't get much acceleration. You get a very low acceleration. That's not good. If you have a very lightweight sail and spacecraft, you have a higher acceleration, which is what you want. So that's called the characteristic acceleration. All right. And the characteristic acceleration is normalized at 1 astronomical unit. Because as I'm flying my sail of a given size, given mass system and go closer to the sun, more photons, more thrust, higher acceleration, but it didn't change its characteristic acceleration. And that's the number we want to specify when we define space missions, because that tells you how well your system is going to perform. And it's a way of measuring the performance of one sail system against another. But of course, nature doesn't always cooperate and let you have a perfectly flat sail. Sails have to be folded up and packaged and deployed in space. Otherwise, you wouldn't get them on the rocket, because these sails are typically hundreds of square feet in area, if not larger. And the sail, when it's deployed with big booms or however it's deployed, will not be perfectly flat. You might have a slight concave shape. You might have a slight potato chip shape after deployment. And that means that the thrust will not be exactly as it would be if it were a flat plane. So no sail is perfect. They're not ideal. You have these real world uncertainties in the shape and the direction with which the light reflects from them that you have to take into account. We have models to predict that, and some of that's been measured in space by scientists. Now, there's something else to be aware of, and that is if you're out in space and the sunlight falling on this is constant, unless your center of mass of your system, of the sail plus the spacecraft, is exactly in the middle of the sail, you might get a little bit more sunlight falling on this side of the sail than this side of the sail. And over time, that would cause the sail to tip over, which means you have to do something to prevent that from happening. Typically involves a maneuver, some kind of propellant, which you don't want to do. So the ideal sail will have the center of mass at the center of light pressure, so you don't get these unwanted torques. It's impossible to get it exactly. And how sensitive this is for sails that are about 1,000 square feet and up, if you're off by just a few millimeters, then you would eventually lose control of the sail. So you have to trim the sail, being able to move its center of mass versus its center of pressure to keep that balance so you don't lose control of the sail. Now, the way we do that is we put something called an active mass translator. And it's basically just an XY translation table that moves the sail either up or down or back and forth relative to where the spacecraft is. If the spacecraft is my hand, we have an XY table with a motor, and we'll shift one down or up compared to the other, and that lets us trim the sail. So that's how you control that any offset of the center of mass versus the center of pressure. A little bit more physics, then I'll get into some of the fun stuff. But if you're a physicist or you're an engineer, you probably like this stuff too. So Les, tell me, why is a sail more efficient going toward the sun than away from the sun? It's not intuitive at all, and I'll explain why. Don't forget that everything in space is moving. So when we launch a rocket from the Earth and we launch it in the direction of the Earth's motion, you're launching with the Earth's velocity already given to the rocket. The Earth goes around the sun at about 30 kilometers a second. So any rocket we send into space has an initial velocity of about 30 kilometers per second, plus whatever the rocket gives it as it orbits the sun. So once again, I'm looking at you. You're the sun. I'm flying around you in this direction. So I launch my sail and I'm moving like this. If I tilt my sail so that I get a net thrust in the direction that I'm already moving, I get a little bit of force pushing me out, and I get a little bit of the force which is accelerating me in the direction I'm already going, which means I increase in velocity. As I increase in velocity, I spiral out from the sun. Okay? Now, if I tilt the sail the other way, well, let me tell one other thing. And as I move away from the sun, the intensity of sunlight drops according to what's called the inverse square law, which means if I take the sail and I double its distance from the sun, it's not 1/2 the sunlight or 1/2 the thrust. It's 1/2 squared, 1/4 the sunlight, 1/4 the thrust. So a sail loses effectiveness for thrusting pretty rapidly as it moves away from the sun. But you do that. We can make sails do that. If you launch a sail and you tilt it this way so that your net force is opposite the direction you're moving. Remember, you're launched into space, 30 kilometers per second of the Earth's velocity plus the rocket. Now you start slowing down as you orbit the sun. Well, what happens when you slow down is the sun's gravity starts pulling you in. As it pulls you in, that inverse square law works for you. You get more light falling on the sail and you increase in thrust. And what that means is if you're halfway to the sun from the Earth, you start at 1 AU at the Earth. By the time you reach half an AU, you don't have twice the thrust on the sail. You have 4 times the thrust on the sail. So what that means is, totally counterintuitively, a solar sail can actually take a spacecraft and spiral it toward the sun faster and more efficiently than it can send one into deep space. Totally counterintuitive and not what most people would think. Most people, when they first think about a solar sail, think the sun's only going to push it away, and it would if we weren't moving. But because everything's moving, you can actually pretty easily take a sailcraft and spiral toward the sun. Now, how big is this thrust, you ask? It's not much. If you were to take a 100 square meter sail, which is roughly 2 football fields, and you have a bright sunny day, clear skies in New Jersey, not a cloud in the sky, it's cold, it's wintertime, it's dry air, great weather that I'm sure you astronomers have all the time. Not. And you take at noon, you measure the force of sunlight on this 100 by 100 square meter, 100 meters by 100 meter square sail. It's roughly the same force that you would experience in your hand due to gravity as a quarter and a penny on your hand. It's not much. But the key to making a solar sail work is it's always thrusting. It doesn't run out of fuel. And as a consequence, the spacecraft that we use, which are typically lightweight spacecraft, because if they were heavy, you wouldn't get much acceleration. So let's say no more than about 150 kilograms for a sail that might be 1,000 square meters or more. Pretty decent. You actually can do better with a sail than any other propulsion system packed into the same volume. It beats chemical, it beats electric propulsion because they all require fuel and lots of it. And a sail can continue to thrust as long as the sun is shining. And that's why there's interest in solar sails for some pretty interesting missions in the inner solar system, and why I'm interested in them ultimately to take us to Alpha Centauri, which I'll get to in my talk a little bit later. So let's talk about the history of solar sails. Solar sails, actually, we knew that light had momentum. That's been known for over 100 years. But we really didn't measure it until early in the space program. And the first time it was actually measured in space was near space, Earth orbit, low Earth orbit, with the Echo balloons launched in 1964. These balloons were packed, I don't know how well you can see this little blip right down here next to this man is what this balloon was packed into. But it was launched into space. A little bit of pressure inside went a long way when you're in near vacuum and inflated this big silvery balloon. And they used that to measure as it re-entered the atmosphere, atmospheric density, upper atmospheric winds. It had good radar reflection characteristics, so they could track it pretty accurately. But there was they had to take into account that when the sun was shining, there was also solar photon pressure acting on this balloon that was applying a force to it that they had to take into account to get accurate measurements of what was happening in the atmosphere. So that was really the first space measurement and space use of solar photon pressure for some kind of thrust. Now, these large lightweight reflectors that are flat plane sails, like I talk about here, there have been several of those that have flown. I write about them and talk about them in my book, Solar Sails, which I had on the cover there. The first for the US was NanoSail D. That was a project that I led at NASA in 2010. And we flew a 10 square meter solar sail in Earth orbit. Didn't go anywhere. It was just a deployment test. And we measured its characteristics, and it eventually returned to Earth and burned up. In the same year, the Japanese, being much more ambitious than us, launched a sail that was about 200 square meters into interplanetary space, and it was called Icarus. I have a video to show you. Well, it's not really a video. It's a series of still pictures that I'm hoping is going to play. There we go. They had a small spacecraft on board that they threw overboard to take pictures of the sailcraft as they flew away from each other. So these are pictures of the Icarus solar sail from Japan as it was flying in interplanetary space. Now, this project did not have controlled thrust to go to a particular demonstration. It too was a deployment demonstration, but they also wanted to show that they could control the sail. Hang on. And not have that problem of the momentum mismatch causing them to lose control of the sail. They did not, and the mission was very successful. Those of you who study Greek mythology might wonder if something got lost in translation to Japan. Because if you recall, Icarus was the son of Daedalus, and they were trapped in a tower and sought to escape. So they put on waxed bird feathers to themselves and leaped out the tower to fly away. Icarus, being a teenager, decided he wanted to fly too high toward the sun because it looked pretty cool to do. The wax melted, his feathers flew off, and he crashed and he died. So I had to wonder why they named their craft Icarus. And fortunately, they weren't jinxed by the Greek mythology, and it worked beautifully. Now, our next solar sail mission, which I led in my day job, we were jinxed. It was the Near-Earth Asteroid Scout. It was launched on the Artemis 1 mission in November of 2022, and it was a culmination of a 6-year effort to build a sail that was 86 square meters, about 925 square feet, attached to a small spacecraft that was about the size of a boot box that was going to take a camera and study asteroids. The spacecraft went into space on Artemis 1, and it never called home. We were unable to establish radio contact with it, and it never sent any data back to the Earth. Are you all still with me? Can you see the slides still? I'm hoping.
Yeah, we can still see it.
Okay, you still see the Near-Earth Asteroid Scout. Okay. There we go. Because usually it's got like a red glow around it that tells me you can see it, and for some reason that screen doesn't have that tonight. Now, solar sails are really good for a lot of things. As you know, there's a lot of interest in returning to the moon right now. There's a planned flight of a crew that NASA will launch in the next 2 years on the Artemis 2 mission that will carry astronauts on a flyby of the moon, similar to what we did in Apollo 8. And it'll be the first time humans have left low Earth orbit since 1973. And that is planned to happen in about 2 years. So there's a lot of interest in the US, Europe, China, and Asia about going to the moon. Lots of private landers have recently landed on the moon. There's interest there of using solar sails in orbits around the moon to loop continuously among the Lagrange points and also circling the moon to take pictures, provide data relay back to the Earth, and do science in support of our exploration of the moon. But perhaps the biggest near-term interest in the sail is by NOAA, the weather people. They are responsible not only for terrestrial weather, but they're responsible for space weather. Now, space weather sounds kind of strange until you realize that on that first or second slide that I showed, you have this constant stream of protons coming out from the sun, and that is the solar wind. Well, when the sun has a coronal mass ejection, that's essentially the sun burping a blob of protons out into space that's bigger than the Earth, traveling outward from the sun toward the Earth. And the issue is when that radiation gets here, it can destroy satellites, it can affect the power grid here on the ground, and wreak havoc on the communications infrastructure. So these utilities and spacecraft operators need as much warning as they can of these solar storms so that they can shut down certain networks, they can power down spacecraft. NASA spacecraft actually reorient to put the more dense part of the spacecrafts facing the storm to protect sensitive electronics from radiation. You only have about 20 minutes to 30 minutes warning, okay? About 30 minutes warning for these storms. And that's because we have spacecraft at the Earth-Sun Lagrange point, and simplistic way of thinking about what that is there, the Earth has gravity. We're attracted to the surface of the Earth. That's why we don't float away. The sun has gravity, which is why the Earth orbits the sun, because that's why the Earth doesn't float away. Well, common sense would tell you there's probably some point between the Earth and the sun where the extremely massive sun's gravitational pull is offset by our gravitational pull. If that weren't the case, when the sun was overhead, we'd all be falling into the sun, but we're not. Our Earth's gravity keeps our feet on the ground. So when you go out into space and the Earth's gravity starts getting weaker, the sun's gravity starts getting stronger, and you eventually reach a point where they're roughly in equilibrium. And this is a crude explanation, it's not completely technically accurate. But that point is the Lagrange point 1, L1. And it always is between the Earth and the sun. So as the sun is here and the Earth is here orbiting, it's always in the same general location between the two. So when the solar storm reaches L1, protons, which travel slower than light, they send a radio signal back to the Earth that says there's a storm coming. Okay, about 20 minutes notice. With a sail, you can take a spacecraft and go closer to the sun than L1, and you get the storm reaching you earlier because you're closer, and you can improve the warning time by about 50%. So we can give 30 minutes warning instead of 20. Now, for spacecraft, that's really important, but it's also going to be important as astronauts venture beyond low Earth orbit for the first time because they don't have a lot of protection from this radiation. And they need as much warning time as they can to get to the shelters that these spacecraft will have, where they basically get in a storm shelter, even in a spacecraft, close the door, and ride out the storm. And so we want to give them as much warning as we can to give them time to get in, and a sail craft could give that about 30 minutes warning time as opposed to 20. So NOAA are the most interested in the solar sails in the near term. Now there's a tech demonstration that NASA is developing that I was the lead for. I'm no longer the lead for this. That will demonstrate the sail needed to do that warning, and it's called Solar Cruiser. It'll fly in about 2029. And hold on to this, the area of this sail is over 17,000 square feet of this 2.5 micron thick material. So it's really big, okay? It's going to go there. Well, this is another mission you can do. I should talk about some of these other missions. I'm going to skip that one. The big interest in sails comes from solar physicists. I'm sure in the astronomy club, some of you have the right filters and you do astrophotography of the sun. And you get some great pictures of sunspots. We do that. I have a friend who's got one of these telescopes, and he set it up in the parking lot at work. And we all came out one day when the sunspots were real active a few years ago. Great stuff. But did you know that we don't see the north and south pole of the sun? We're orbiting around the ecliptic plane, which is essentially around the equator of the sun. And the highest we can see is about 70 degrees solar latitude. So what's happening between 70 and its poles is unobservable from the Earth. And all the spacecraft we launch, except for one, basically orbit in the ecliptic around the sun, and they can't see what's going on at the poles. Now, try to imagine being an Earth terrestrial weather forecaster and being able to forecast terrestrial weather if you don't know what's going on at the North and South Pole. You can't do it, not very accurately. So there was a mission several decades ago called Ulysses, where they sent a spacecraft out to Jupiter where it did a gravity assist, which changed its inclination, flung it back over the sun, and they had about 90 days of data. But it wasn't an orbit around the sun. It was just a flyby, and no one's looked at the sun's poles since then. The reason the scientists are interested in a sail is you launch from the Earth's equator. But remember, I said if you tilt the sail like this, you get a thrust vector that takes you up. So over time, you can crank your orbit, and instead of circling the sun's equator, you can circle its poles and do constant viewing back and forth of the north and south pole of the sun. So heliophysicists want to do that kind of mission in the future. Another thing that's a real interest for the future is climate change mitigation. And I won't go into a lot of detail on this because this is a topic in of its own right for a talk. I could give this about an hour long. But if you've been following the climate change issues, you know that the concern is that we are no longer in energy balance, and that we're trapping, thanks to carbon dioxide and other greenhouse gases, trapping some of the incident solar energy that falls on the Earth and keeping it in the atmosphere instead of letting it be re-radiated back into space. and it's too much carbon dioxide for all of the biota on the Earth, the biologics, to absorb. So that builds up in the atmosphere and we're trapping heat. Okay, we all know that. We've been hearing that for 20 years. So what do we do about it? Well, there isn't much we can do on the ground. And the reason is this particular chart. And I won't go into a lot of detail except to point out that the colors indicate the carbon emissions of different countries. And you can see that the US and Europe, for the most part, have been down here at about 5 gigatons. Here's the EU is green. They're down to about 4. We're at about 5. Our total carbon emissions have gone down over the last 30 years. But this red line is China. And they now emit more than the US and Europe combined. When Al Gore wrote his book 20 years ago, Earth in the Balance, and this all came to public attention, China's emissions were less than the US and Europe. Now they put out more than us combined. And what that means is every citizen of the USA and Europe could all vanish tomorrow, and we'd be in worse shape with carbon emissions than we were 20 years ago. So what does this have to do with solar sails? Well, there are groups that are looking at deploying very large solar sails at that Lagrange point between the Earth and the sun to block or divert some of the sunlight so that it doesn't reach the Earth to heat the atmosphere. You can deploy sails to actually block a little bit of the sun. You would not notice this with your eyes. About 1% of sunlight diverted would cool the Earth by about 1.5 to 2 degrees C. Is this something we can do today? Absolutely not. The sails are too big. You require lots of them. It'd be very expensive to do. But if climate change is an issue that we want to try to mitigate, and if it's really happening like we think it is, then this needs to be in the trade space of things we might do. It's an application for sails. NASA's not doing that. There's no group that I'm aware of that's doing that, but it's an interesting thing to think about. Now, what got me interested in solar sails is going to be something that you're going to say, well, wait a minute, Les, how can you do this? Because you'd be traveling out instead of in. And that is to use a solar sail for rapid solar system escape, potentially reaching another star. I read about solar sails for the first time in high school. I read a science fiction novel called The Mote in God's Eye in the 1970s while I was in high school, and it was written by the great science fiction writers Larry Niven and Jerry Pournelle. The premise of the story is there are alien invaders coming toward the solar system, and they're getting here with solar sails, not propelled by sunlight, but by high energy lasers. Lasers emit photons. Lasers have a focused beam, can be very high power, many times the power of sunlight, and that can accelerate your sail. Or you can build a big sail, really big, think a square kilometer, and deploy it inside the orbit of Mercury and get enough velocity to take a small spacecraft to Alpha Centauri in only a few hundred years. That's huge because right now with chemical rockets, a similar voyage would take about 70,000 years. It's one of many topics I explore about realistic interstellar travel in my book from Princeton University Press called A Traveler's Guide to the Stars. It's a nonfiction popular science book that I wrote and was published in 2022. It's my best-selling book now, actually. It's in 7 languages, but it's all about how we might go to the stars and solar sails to take us to the stars, augmented by high-energy lasers placed throughout the solar system to keep accelerating them as they leave the solar system, could potentially get a robotic probe to the Alpha Centauri system or the Proxima Centauri system in less than 100 years, traveling at about 10 to 20% the speed of light. It would be amazing, and it's probably doable, although not right now. So as we get to the last part of my talk, I want to give you an idea of how real these sails are. This is a picture of that big sail that's going to fly in 29, the Solar Cruiser solar sail. It's broken into 4 quadrants, all of the same size, and each of these quadrants are like pieces of a pie that are put together, 4 booms. Each boom, you'll see the picture in a minute. I'll go ahead and go to the picture. No, I'll go back to it. As you look at this picture, this box right here where my cursor is where the sail is stored. The sail, all 17,800 square feet of sail, is flattened out and rolled onto this spool. Down here in this bigger box are 4 booms. These booms are a carbon composite material that flattens and rolls. And when it deploys, it rigidizes just like this. And each of those booms are 100 feet long, and you can fit 4 of them in this box. That bolts onto the top of the spacecraft, and that's the sail propulsion system. Now, we've done several deployments. We deploy 1 quadrant at a time because finding a building that doesn't have pillars in the wrong place, especially to deploy the entire sail, is basically impossible. We have to find a building that's 18,000 square feet that has no support structure on the inside, a suspended dome. I think there are some NFL's enclosed stadiums out there that we could use, but we haven't done that. So we've only deployed 1 quadrant at a time. So this is 1/4 of 17,000 square feet deployed, and you can see the third person from the right is me over against this wall. You see here a picture of the boom as it was being fabricated. It's 100 feet long. This is how the sail is fabricated in strips before it's folded and rolled on here. Now, to give you a sense of what this looks like, I'm going to show you a time accelerated video of a recent test of the deployment of this quadrant. So let me bring it up. There we go. It's a pretty impressive video. You can get that out on the internet. It's pretty widely available. It's on YouTube. I think our prime contractor that NASA used, Redwire, has it on their website. So you can get that and replay it out there if you want to. And here's another picture of one of the deployments. And again, that's me, the third one on the right, standing over there. Now, I have a vision for solar sails, and this is kind of where we've been, and then I'll show you where we're going. In the world, mostly in the US, although Japan and Europe have also been building them, this is kind of the size evolution of sails. The first one to fly was NanoSail D, 10 square meters in the NASA series. Then the Near Earth Asteroid Scout was 86 square meters, which is roughly 100 square meters, about an order of magnitude larger. There's one in orbit now that's ACS-3. It's in Earth orbit. It's about 80 square meters, close to 100. And this is how big the one that will fly in 29 is compared to those we've flown before. So that gives you a sense of the scale. But to build the sails that I want to build, and that I hope the people at NASA build, or someone in the world builds as the technology matures, are going to be sails that will give us ever larger capability and eventually allow us to reach the stars. So I created a roadmap. If I'm a good bureaucrat, I created a roadmap. I said every sail generation that we fly needs to be an order of magnitude bigger than the one previously. So it's like Moore's law for computers in terms of microprocessors, but it's Less's law for solar sails. So here's how we're doing. We had the first generation sail in 2010, 10 square meters, NanoSail D. Near Earth Asteroid Scout and ACS-3, which is in orbit right now, are about 100 square meters. We've designed the 1,000 square meter solar cruiser sail. Then after that are only the 10,000 square meter, the 100,000 square meter, and the square kilometer sail, which is 1,000,000 square meters. Now, what's kind of cool is when we started this, the material required for this square kilometer sail did not exist. And we called it unobtainium because the stress and the tension that had to be held under any material we had today to stretch it, keep it under tension, and keep it flat would have ripped. But in 2004, the material called graphene was discovered. The discoverers won the Nobel Prize for that in 2010. Graphene, which I ended up writing a whole book about, I thought it was so fascinating, is a form of carbon that's a single atomic layer thick sheet of carbon. Carbon, carbon, carbon. Totally perfect sheet, totally flat, one atom layer thick. It's 300 times stronger than steel by weight. What that means in a practical sense is this one atom layer thick sheet of graphene. Today, we can only build a few millimeters, not even quite a square centimeter of this. But if you were able to build one large enough, you could put an elephant on it in Earth's gravity and it wouldn't break. So when this graphic was developed, this material for this big sail as a substrate to put aluminum on or something else reflective did not exist. It now exists. So technology marches forward and eventually we'll get the capability to do that. Now I have to give credit to the person that inspired me in my life and was an early mentor in my career, Dr. Robert Forward. Great inventor, innovator, is the one who published all the seminal first ever papers about using solar sails and laser sails to go to the stars. Larry Niven and Jerry Pournelle read his technical papers before they wrote the book that I read. Bob Forward died, unfortunately, in the early 2000s. For those that are interested, he was also a science fiction writer, and his science fiction was really, really good, very innovative stuff. Still in print. I think some of them still in print today. So I give credit to him. And this artist concept is of that laser-driven light sail going to the stars. Now I'm going to conclude before I get to my crass commercial message at the end by relaying a story I want to give you about what motivates me in my career, in my science fiction writing, and in my social media outreach and speaking engagements like this that I do. And the motivation came about in one of those NASA management meetings. And if you're at a big company, you probably have these same things where they get the leaders together and you have to do all these exercises in leadership and the Myers-Briggs personality test and all that kind of thing. But they ask us to write down what our career goal was. And so a lot of people had really good things written down, you know, to be the best manager, enable my people, do innovative things, which is nothing wrong with any of that. But when I thought about it, my career goal is something that won't be seen in my lifetime. And it is this, that when the history is written of the first extrasolar settlement by humans on a planet orbiting another star, that when they write their history and they recount all the things that happened that enable them to get there, that the work that I've done is a footnote in that book. That's what motivates me. And what I'd like to do, I don't know what that footnote will be, whether it's the work on solar sails or nuclear propulsion or other things I've worked on there, whether it'll be some young person reads one of my science fiction novels and goes and pursues a career and ends up doing something great or innovative, and that leads us going to the stars. I just want to be a footnote. So on that, I will take my last slide, show you some of the books that I've written. The one that I've spoken about most this evening is my book on solar sailing. But I also have written the one I talked about, Traveler's Guide to the Stars, and then some of my science fiction novels are here in case anyone's interested. These books are widely available, ebook, print. You can also get them in audio book, Amazon, Barnes & Noble. You can order them at just about any bookstore. So with that, I'll stop and take questions.
That was great. Applaud.
Yeah, love.
Actually, I have questions, but I want to wait. Do we have questions in the
Yeah,
audience?
that's just real quick. Everybody, people that are online, you can take yourselves off mute if you want to ask questions.
Looks like Pranesh has a question.
Yep, if you
Yes, I have a question about so when we go to these solar new star systems, most of these star systems are binary and trinary star systems. They're not a single star system like here in our solar system. So how do we ensure that, like how you're explaining that chaos when the light hits the solar sail on its thin edge and not on the far edge? How do we ensure that doesn't happen on like these binary and trinary star systems?
You know, I've been talking about solar sails for 20 years, and that's the first time anybody's ever asked me that question. So, this one I'm gonna tell you right now, the sails are really going to be used for the interstellar. First off, the precursor missions, which will be flyby missions, where they're going to fly through the solar system and take data. Um, if they're accelerated by a laser, then those stars will decelerate them, and that will affect the sail. I have not done the analysis to determine and understand what the three star bot problem, the three body problems. If you want to go to the popular TV series and everything else, right, of the Centauri system, the three body problem would be in gravitationally or from the sunlight reflecting from the sail. I think all of those things would complicate the flyby maneuver. So that is a question that the future mission planners will have to look into, and I am going to make a note of that after this call tonight. I don't have a quick answer for you other than I would have to go to my experts who are the experts on doing mission analysis, the astrodynamicists. And I will guarantee you one of them will scratch their heads and say, you know, that would be a good paper to write. So you may have just inspired a new technical paper or a journal article somewhere.
All right, thank you. I might be the one writing the research paper. Who
Go
knows?
for it. Do it. And send me a copy when it's published, would you? I'm serious. You got my contact info.
All right, I got it.
yes, sir, go ahead.
Yeah, one of the things that Pranesh asked about in passing is how would you decelerate? Because, you know, any real interstellar mission, for the first half, you're accelerating, and then you've got to be able to decelerate so that you stop at the objective you're reaching as you reach it. How would you do that with a sail? Is that possible?
If you're only using sunlight to accelerate out of the solar system, and you're doing that using solar pressure that is many times what you experience at 1 AU by deploying your sail close to the sun to give you a trip time of a few hundred years, which instead of, you know, if you had a laser, you could get that down to under 100, but if it's 300 years, then you could theoretically do a close flyby of the Alpha Centauri system equally close to that star and use the photon pressure to slow down. Okay. I personally believe the early probes will be just fast flybys with cameras to take pictures to send back.
I get
Now,
that. That's the way to start for sure.
yeah, in the farther term with crews, we don't know how to build a big enough sail and to get there with people. I mean, we would be talking sails the size of Texas. Okay. So that would be a real challenge. I think when we start sending people to the stars, we'll probably shift to other propulsion systems, things like fusion and antimatter driven starships, which are equally physically possible, although we have no idea how to engineer them today.
Yeah, it wouldn't be, maybe not people is the first thing you send machines to explore, and you still got to be able to decelerate. So, but that, I guess you can do that.
Well, the problem, and this is something else I did just for fun. If you have a spacecraft that only weighs a kilogram, let's assume we get really good at miniaturizing spacecraft and power systems, and we get everything down for an interstellar flyby mission, you know, in 100 years from now, it's no heavier than a kilogram. Well, a kilogram is about the same weight as a pineapple. So think about sending something about the size and mass of a pineapple to the stars. If you send it at just 10% the speed of light, and you miss the flyby and you hit the planet, the kinetic energy equivalent is 7 Hiroshima class atomic bombs. So you will inadvertently start the universe's first interstellar war, right? Here come those humans and they attacked us, right? So you got to be careful. And that's a potential worry, because a lot of people spend a lot of time thinking about something called the Fermi paradox. You know, why haven't we seen evidence of life at other stars? Why haven't we been visited? But if these interstellar probes are being sent out into the universe by any civilization traveling at 10% the speed of light, that could be devastating. Now, the probability of hitting something is very low unless you have really good aim, right? But you know, interstellar travel is an immense energy intense endeavor, and it's not without its risks.
Other questions? One in the back. Speak up, please.
How do you repair the sail if it gets a hole in it?
Good question. You don't. It's really, this is also kind of interesting. Earth orbit, you don't deploy sails much. They won't last long because of the orbital debris. But when you get out in deep space in the solar system, and it gets better in interstellar space, you know, I go back to Douglas Adams. You know, space is big. And it's mostly empty, but there are micro dust particles and micrometeorites, things up to the size of a pea or smaller, that are traveling at like 21 kilometers a second. Well, if something traveling 21 kilometers a second hits my cell phone, it's going to explode it like a bomb went off. And the reason for that is this is kind of massive. And the kinetic energy of that particle hitting it is going to interact with a lot of mass and slow down a little bit before it pops out the other side. And that slowing is going to be manifested as heat in a small volume. Well, when a lot of heat is expanding out of a small volume on the Earth, we call that a bomb, right? So my spacecraft, if it hits it, is going to explode and it's going to suffer a lot of damage. The sail is very thin. And as a consequence, that particle traveling at 18 to 21 kilometers a second hits it and is through it and hardly loses any energy at all in the interaction. As a consequence, it just makes a tiny hole. And to validate those models, about 20 years ago, the engineers took pieces of sail, put them in a hypervelocity impact chamber, which means they had a gas gun, and shot particles out at 18 kilometers a second and smacked it. And sure enough, it didn't destroy it, it just poked a little hole. And so sails today have ripstop like parachutes in case they get a tear, but they are designed to suffer up to 3% area loss over 20 years and still operate.
On that same topic, between photons transferring their energy to the sail and proton storms,
Right?
okay, I would guess that there would be, and such a thin film, I would guess that there would be erosion over.
Not much. Not
Not
much.
much.
It depends on the material. We had NASA had several, these papers are published, tested several materials, and some of them eroded away. Some of them, when they were exposed to the sunlight, the ultraviolet light, the electrons and the protons, they got brittle and turned to ash. But the material that's used today is a polyimide, especially manufactured for use in space, that's very resistant to that kind of damage. And the company that makes the sail is the same company who made the sunshade for the James Webb Space Telescope.
I see.
Okay. It's not the same material that's in the sunshade, but it's a cousin. And so this material is very resistant to radiation. Good question. And that was a big concern and required some innovation.
Couldn't, is there any energy in terms of electrical energy that can also be pulled off of the solar sail?
Oh, yeah. There's a graphic that I had that I didn't talk about it, but in orbit right now is a little spacecraft, and I'm a co-investigator on the flight. It was my idea, but I was busy building solar sails, so we handed it off to one of our newer employees to be the principal investigator. His name's John Carr. It is a solar sail that has thin film photovoltaics adhered to it. So it's these flexible, thin photovoltaics like you're in calculators when people had calculators or in little solar powered handheld devices. and it's deployed. And so not only can it get thrust from reflecting light, but a little bit is absorbed and turned into electrical power.
I see.
There are also companies now that have figured out how to use printing to print solar cells on the sail directly, and then etch metallic traces that are insulated from the sail itself for conducting the power that they generate back to whatever device is going to use it, and it's all printed on the sail. So I can see a future, and then if you look into something called quantum dots, you can actually build spectrometers, do spectroscopy that is done in painted and printed material on the sail. I envision a future where there is no spacecraft, and the spacecraft is the sail, and everything about navigating, controlling it is built into the sail, and the science instruments themselves are printed on the sail. So that is something that I would like to see people more actively work on, because theoretically, I think it's possible.
One question, I know it wasn't the main topic of this, but I can't picture how laser, if you're looking at interstellar travel, then you're looking at laser-driven sails.
Yes.
I can't picture how that's created. Where are the lasers? How does that work? And lasers draw power.
Oh,
So,
you got to just dream, man. You're not dreaming big enough.
yeah, I know.
Okay, if I'm going to do an interstellar sail, I can't build it today. I remember I don't have that graphene big enough sheet, so we're still decades away. But
Okay.
if you build that, why right now here in Huntsville, Alabama, the Army, to protect its troops on the ground from drones and from mortars, has on the back of Army trucks 65 kilowatt solid state lasers. Okay. The Navy is putting these on ships for point defense against incoming missiles. These lasers are very high power, and I've seen numbers that are much higher than 65 kilowatts. If we can get these up to megawatts
Hmm.
and put them on a spacecraft with their own dedicated power source, put them strategically in the solar system, deploy the sail close to the sun. As it reaches Venus orbit, a laser's there and it puts more light on it than just the sun puts on it. Got another one at Earth orbit as it flies by, another one toward Mars to zap it yet further still. And you have a network of these going out of the solar system, handing off the beamer from one to the other as the sailcraft leaves the solar system.
Okay.
Okay.
Oh,
So
that's how you'll do it.
that's how you'll do it. It's not going to happen near term. Hey, wait a minute. You got to
sorry.
dream, man. You got to dream.
Sorry.
Les, I have two questions.
Yeah.
So one is, does solar sail technology now replace ion drive propulsion?
No. They all have their own niche. Solar sails are really good for small spacecraft that operate in the inner solar system right now. And a solar electric can't keep up if for some of these missions, like the solar storm warning, on a comparable size spacecraft, if you used a solar electric thruster, you would run out of fuel in about a year. And NOAA wants to have a 20-year lifetime. So a solar sail is the only thing that can do that. Now, for bigger spacecraft, heavier spacecraft, the force of sunlight is not enough to allow us to have a heavy spacecraft and a high acceleration. So the thrust would be really low, and the SIP system outperforms a sail on spacecraft that are heavier than about 100 to 150 kilograms.
Okay.
So no, it's not a replacement. I think one things I've learned is there's no one size fits all spacecraft propulsion system. They all have a niche. And the niche for solar sails is lightweight, high delta V, high performance, very lightweight. Or if you ever want to go to Alpha Centauri, it's really the way to go if you don't want to build an antimatter or fusion drive for robotics. Yeah.
Thank you. My second question was, as the solar sail deploys, does do photons from other stars contribute at all to the mass it's adding for propulsion?
You mean the thrust that it gets?
Yes, yes.
Okay. Well, theoretically, yes, but it's really small. It's so small as to be negligible, really. Yeah.
All right, thank you. Are there any questions here?
I just have one thing I remember from a few years ago. There was talk about sending, you mentioned Proxima Centauri,
Absolutely.
sending some small, very small probes out. Was that ever done? Or
No,
no,
it
it
was something
wasn't?
called Project Starshot, and it was going to be a laser-driven sail mission like I described here, but the lasers were going to be on the Earth,
Hmm.
and the sailcraft, instead of weighing a kilogram, their goal was to build spacecraft that weighed a gram. Okay.
Okay.
And it was just not doable in the time frame that the funders were hoping to be able to do.
Yeah,
They couldn't get the material, they couldn't get the laser, and they don't think they could get the spacecraft miniaturized that much. So that project was put on a shelf.
I see.
Excuse me, I have one more question.
Sure.
So, because we're sending the spacecraft, the sails into hot weather near the sun, and then bringing them out of orbit for interstellar travel in these cold, freezing temperatures, wouldn't that impact the sails because heat expands these sails, and then the freezing temperatures like condenses these sails? So, wouldn't that have any impact or damage on these sails?
Probably not. We've done those thermal analyses and tested the materials for those environments, and they survive pretty well. I can't it actually, yeah, it's not that big of an issue. It's more of an impact on the electronics and any sensors and moving parts that the sail has than the sail itself. The sails are actually pretty robust. They are most likely to be damaged in that room where they're being fabricated. That's where they can be most easily damaged. The second place they can be easily damaged is in the rocket as they're going to space, because rockets aren't smooth. They're accelerating as they shake, and those rapid, short intensity accelerations can damage anything. And you have to really test things to make sure they survive that. And that's a risk to the sail. And you also, something that not many people think about, you're going from, in 8 minutes, you're going from 1 atmosphere pressure to zero pressure or close to zero pressure. And that means any air that's trapped in the folds of the sail will cause the sail to blow up like a balloon, which could damage it, like that echo balloon. And so in the folding pattern that people came up with for the sail, they fold it and there are pathways for the air to rapidly escape so it doesn't blow up like a balloon. All
Right.
of those things are more likely to damage it than actually the space radiation environment itself, whether that be heat or cold or protons, any of those things.
All right, got it. Thank you.
I had a question.
I just have one little thing. And I remember as a kid, I remember Echo.
Oh, you do? Okay.
Watching, I remember Sputnik. Hey, hey, hey. Anyway, uh, what was the mission of Echo focused on the material, or was it mostly just to reflect communications signals? What?
It was used for a lot of things. It
Oh,
was
was
used to measure atmospheric contours as it was traveling in low Earth orbit, because you're not out of the atmosphere. Even the space station technically isn't out of the atmosphere.
yeah.
The space station experiences about a Newton of drag thrust from atmosphere, even at 400 kilometers altitude. So you're not at zero. So the big Echo balloon, being lightweight and large area, it slowly lost altitude and re-entered. They reflected radar from it. They used it to test communications. They measured solar photon pressure. I think every possible measurement you could make with the Echo balloon was made at that time.
I see.
Yeah.
And that gets me to the last question. Yeah, you had mentioned, of course, that drag in space.
Yes.
And you had addressed that. You answered a question earlier, but it seems as though the cumulative effect of I mean, I picture this as a rectangular column, and if we took a rectangular column uh, and we looked at how many particles, it seems as though there would still be enough to um, significantly reduce the thrust of the photons in that.
No, no, the atmosphere you worry about beyond about 1,000 kilometers, there is none. And so when you get out of Earth orbit and you're in interplanetary space, I
Mhm.
mean, it's vacuum
It
except
is.
for those micrometeorites that are out there.
Okay.
So, and when you get to interstellar space, I don't want to get the number wrong, but it's something on the order of like 1 hydrogen atom per cubic meter.
Okay.
Okay.
All right.
So
Now,
there's
there.
really not much there.
Oh.
It's pretty empty.
We do have one other question here.
Well, I was just surprised that we've never seen the poles of the sun. So what did we learn in those 90 minutes of data?
I am not the person to ask that question. I'm not a solar physicist. That's a good question. But I do know that whatever they learned, they've been using it because that's all they've got. I don't know. That'd be a good one to look up. I think it was the Ulysses mission, if I'm not mistaken. You might Google that. I could have the name wrong, but I think it was Ulysses.
Thank you.
I think we're good with questions here.
Les, thank you so much. This
Thank
is
you, Les.
fascinating. It's a topic we've never
Wonderful.
talked about.
Well, thank you so much for your interest. It was good talking to you all. I loved, as you can tell, I hate talking about this stuff.
Oh, yeah.
It's just awful.
We had to pull it out of you.
You just had to pull it out of me. You all have a great evening, and I hope the weather clears up for you.
And we'll look up your books too. This is
Feed the author. That's always a good thing. All right. Bye-bye. Y'all have a good
Bye
evening.
now.
Good night.
Good night.